I want to welcome you here to our first masterclass presented by For the Love of Bees and Daniel Sherman from Biologics. This is part of the Regenerate Now Learning Together platform that we have been creating with the Urban Farmers Alliance and the For the Love of Bees community over the past month. We're really excited about this new Learn Together platform. If you're part of the UFA, which is the Urban Farmers Alliance, you can get supported via a WhatsApp channel on a daily basis where you can ask a question and via the peer-to-peer mentoring system, get an answer to that question in a timely fashion that you need as a farmer in the field. As part of the Regenerate Now program, we have our new Regenerate Now Instagram, which is an Instagram takeover, which our really amazing Urban Farmers Alliance and these Centres of Regenerative Learning are using. And what they're able to do for a week is introduce you to their farms, tell you about the innovations that they're doing, and learn alongside them as they are learning themselves in the field to really develop this next level regenerative farming system that feeds local communities, embeds food security, local jobs, and is really, we're starting to think of it as a civil defence strategy. The next thing that you can do is join these farmers on a Friday at 4 p.m. where we have a farmer in the field session where that particular farmer gets a 1-hour mentoring session with 3 of the Regenerate Now mentors. This is online, so you're able to join and learn alongside that farmer, and through the chat function actually ask questions along the way. But tonight is our very first public sharing of our Masterclass series. This is a series that we hope to be able to fund over the next year, where we do a deep dive into biological systems, the systems in our soil that enable us to actually, every time we grow a piece of food, rebuild the ecosystem, not destroy it. I am Sarah Smuts-Kennedy. I'm an artist. I'm the vision holder of the For the Love of Bees, and I'm one of the co-creators of the Urban Farmers Alliance. And I'm really thrilled that you have taken the time tonight to join us, and please share this network with anyone that you think might benefit from it. Daniel.
Yeah, good evening. This is as Sarah said, our second run through of this presentation, which we have tweaked since last week. So some of you would have seen some of this, and there's a few changes that I've made, but my background is in horticulture. I've spent my life in it, was born into it, and I guess about 25 years ago, through that process, started looking, having been taught the chemical farming model, started seeing the weaknesses and the problems with it, and started a re-education process myself, which has, as I explain to people today, is if you're interested in soil and you study soil, you become a student of soil for life. No one ever really fully attains all the knowledge because we don't have it. It's something that the science that we're learning about, and what we're going to try and teach you a little bit of today is the latest science, our understanding of what basically healthy soil system looks like and how to manage it. So Sarah, should we get started? Right. So healthy soil, it's all about balance and a do no harm biology first principle. We're going to take you through the process of understanding what soil actually is, which might sound as sort of an unusual thing to talk about, in the sense of, well, soil is essentially the stuff that, you know, grass grows in, and it's the brown dirt sort of material underneath your fingernails and etc. But the definition of what is considered soil varies between these two extremes that I'm showing in front of you. What largely is governing our growing and our management of soil today is the definition here on the right hand side, which is basically what your scientists and chemical industry and farmers, agricultural industry by and large believes is what makes soil and how soil should be managed. And herein lies the problems that we have with our current soil loss of topsoil and the other ecological issues that we have around it. So one, the similarities are here that in both cases we're looking at the parent material or the mineral component being a combination of sand, salt and clay, all those minerals properly balanced. And then on the chemical side here, basically they see that as you need to put in inorganic soluble minerals. The NPK model must be added to this inert support matrix to supply plants with nutrients. We're on the left hand with a definition by one of the fathers of soil science, a man called Hans Jenny. Agrees with the first part, mineral, sand, salt and clay, and all minerals properly balanced, of course, but then soil isn't soil unless it contains organic matter. And that sounds, again, very simple and basic, but essentially treating soil using, we'll show you as we go through this, by treating soil with organic soluble minerals, the fact is the organic matter in our soils is what is causing a large number of the problems, because they've ignored it. They've depleted it. So the soil that we look at as soil today lacks this first component in a major way, which is organic matter. The next critical thing that the soil needs is aerobic organisms. For that soil to function as soil, you need those three components. And with healthy soil, those three components are all present and functioning as a system. With chemically managed soils, you're basically losing these last two. Organic matter is depleted, and organisms like aerobic organisms, that's the beneficial bacteria and fungi, are extremely challenged or in some cases non-existent.
So we have a question already, Daniel, from Prashanti, and she's asking, what is the difference between aerobic and anaerobic microbes, and which ones should we be promoting in our soils? I know that's a very big question for right at the beginning, but I think, why don't we just put it to her now?
As we'll see a bit further on, when we start looking a little bit at microbes, but essentially that is an entire topic for Masterclass. But soil, as we are talking about it in terms of being a healthy soil system today, is an aerobic system. So therefore it thrives in oxygen. So if it lacks oxygen and you create an anaerobic environment, you promote the wrong microbes. So a lot of the anaerobic microbes in the soil system are pathogenic. There is a whole group of facultative microbes which can survive in both conditions, which can be beneficial as well as harmful. But it's a very complex discussion to have. So all I can say is that at this stage is we're looking for a soil system must contain, and this picture here actually shows one of the reasons why the soil system is aerobic, so therefore contains oxygen and support those organisms. And that's why I made that definition, is that when you're looking at soil, you've got the mineral component making 45% of it, but air, in fact, should be making 25% of it. So this thing called air to water, air porosity to water holding ratio. In an ideal situation, you have water and air basically making up 50% of the spaces within that soil structure. But tonight, we're basically going to concentrate mostly on this mineral and the roles that the organic matter plays within the soil. Because without that organic matter, and in that organic matter is made up of humus, which is basically the soluble organic carbon in that, obviously plant roots, and those organisms we were talking about before, they also include obviously the aerobic fungi and bacteria and the anaerobes of the microbial world, but this also includes the worms and the protozoa and all the other organisms that actually make their life in the soil. Does that sort of answer it, Sarah?
Yes, it does. And just to let you guys know that this first class is actually going to introduce a whole lot of concepts that in and of themselves require an entire masterclass. Hence why we're looking at trying to run 26 of them over the year. So if you don't understand something fully, the reason is that we haven't had the chance tonight to go into it in the depth that it requires.
Just so we know, my screen's telling me there's 6 more people that want to come in. I'm not sure what's happening there. Okay, so just to get some understanding of how many of our common soil practices are actually negative, ploughing, obviously in the picture there will be one of them, but essentially some of the biggest issues that we have negatively affecting the soil health, things like monocultures, and that's also going to be part of the discussion around microbial health of the soil and how monocultures relate to that as part of that microbial aspect of the masterclass that we'll do at a later date. Pesticides, herbicides, insecticides, fungicides, including organically certified ones. Anything basically that's been applied in the soil, that's job is to kill, i.e. the side end of the words above there. It doesn't matter if it's organically certified. A copper fungicide is still a fungicide. It is still going to harm soil life. Sterilization, solarization, so using chemical or heat to kill even for just weed control. None of that is positive. Cultivation, tilling, ploughing, rotary hoeing, harrows, ripping, fallowing. That's leaving the soil bare for extended periods. A very common practice in some growing systems where they'll grow a crop. Even here in New Zealand with onions, typically prior to an onion crop, the soil will be bare, waiting for the onions to be planted for anywhere up to 3 months. Anything around 6 months of having no plants growing in the soil can create a thing called long fallows disease, which is basically death of the microbial system. Excess fertilizer and inputs, and that also includes excess inputs of compost. Again, excess soluble fertilizers, we'll talk about soluble nutrients, cause a problem. So all these practices have one thing in common: they harm the microbial life that is the basis of the soil system. All of these are common practices in conventional organic farming and organic farming systems. The soil system from a textural point of view is what this diagram is showing, but essentially as a system, we talk about it as a biological system. It is a living system. It has both mineral and living components to make the system function as soil. The mineral or parent material is clay, which is clay, sand, silt and sand, and that determines soil type or texture. And the graph on the side here is a typical way of determining whether a soil fits in on a textural basis, or whether it's a clay loam, silty loam, a loamy soil, a sandy loam. All has to do with ratios of these individual parent materials in the soil structure. The living part of the soil system, of course, is how the organic matter is made. So to get a better understanding of the parent material, what we're looking at here is essentially sand, silt, and clay are the same parent material. The only really difference they're talking about here is actually in size, particle size. So you have clay being an absolutely, as you say, minuscule, tiny, small amount of size, where you have, which obviously brings soil texture together and closes it up. Silt fits in the middle. Clay can hold a huge amount of water. Silt tends to open it up, and sand encourages the air porosity. But essentially, sand is turning into silt, silt is turning into clay, and sand was derived from pebbles, pebbles from rocks, rocks from boulders. And that process of breaking down that we think of in terms of erosion is actually the result of organic acids from microbial activity that is actually creating that breaking down of those particle sizes. So the beneficial microorganism's job is to harvest nutrients from the soil organic matter in the form usually of carbon, and then from the parent material, from the rocks, pebbles, sands, and silts and clay. They are comprised, I'll show you shortly, of these crystalline structures that are not easily broken down. Those structures contain pretty much all the plant nutrients apart from two, one being carbon dioxide and the other one being nitrogen. The crystalline, so they use everything from boron to phosphorus to calcium, potassium, iron, everything you're thinking of in terms of fertilizer, apart from those other two I mentioned, are all originating from these parent materials. Plants are not capable of directly accessing those nutrients in these structures, and I'll show you why. So what we're looking at here is essentially, if you broke down clay or sand or silt, what you're looking at is a series of these crystalline layers. There's huge amounts of silicon in this process, and the plants can't access this nutrient. These nutrients are trapped within this parent material. So what happens is the beneficial organisms are taking the carbon from the organic matter, and they are using their organic acids from the microbial activity is actually breaking down this parent material, and through some basically very sophisticated organic chemistry, forming the nutrients that the plant will be able to access, which we'll show you in this slide. So in the top, we've basically got these three pools of nutrients in the soil system. The total is if you took everything in the soil and use incredibly strong acids, and to work out what the nutrition, total amount of nutrition was, you'd find there is, and we can show you a bit later how much, there's enormous amounts of nutrition in that soil, absolutely unbelievable, endless sorts of nutrition. The biology is breaking that parent material down, as I was explaining before, and it creates what we call as an exchange pool. So these aren't yet plant available, but in the process, they are more soluble. They are in the process of basically being put together with solubilized out of the parent material, combined with carbon to create these complex carbon atoms that give life to bacteria and fungi. That bacteria and fungi is consumed, and the exudates from those predators are what actually creates the soluble nutrition. And the soluble nutrition is essentially what is what the plant is accessing. So what happens when you start throwing in inputs into soil is you're going to have an effect on one of these three pools. More often than not, the soluble fertilizers, or even in that matter, the compost that you're putting in has a huge amount of soluble nutrition. And what typically happens is that you flood the soluble area of the soil system, which then starts to actually shut down the necessity for the microbials, because the plants essentially, as the plant photosynthesizes and feeds the system carbon, those organisms need to use that carbon to make this exchangeable pool. But if the plant stops feeding carbon into that pool because it's flooded with soluble nutrition, you end up with the system starting to break down. It doesn't function as it's supposed to do. The plant has access to a huge amount of soluble nutrition, but the microbes that rely on the balance in the system start to close down. So there'll be fungi that start to not work. One of our misunderstandings in the early part of science is that we were very good at chemistry because we didn't have the most sophisticated microscopes in the world. When we looked at soil, what we saw was sand, rocks, and pebbles and clay, and we started seeing things like worms and larger organisms, and then later on fungi and protozoa, very big organisms, but we really didn't have the capability of understanding the microbial network in the soil until microscopy became as advanced as it is today. So we started on a process of looking at soil from a chemistry-only point of view. And on the left-hand side here is a range of chemical protocol acid extraction systems that have been developed over the last 100 or so years in modern science to try and understand soil. The first one to understand here is that this first group that we're talking about here is basically designed as a small selection to understand what nutrition is in the total nutrition. So it's extracting using very strong acids, breaking apart the parent material and extracting all of the nutrition to work out how much nutrition there is available. The next group is targeted at the exchangeable, And the last group is targeted, these all sorts of different acid processes and protocols designed to extract nutrition out of the soluble. Now, the thing that to understand here is that when we have a soil analysis and they give us a figure, the figure, let's say it's phosphorus and it says 70 parts per million. The relative, to understand that 70 ppm and what it means, you need to know the protocol of how it was extracted, because the 70 parts per million phosphorus tested with a malic 3 does not mean the same thing if you test phosphorus with a Bray 2 extraction and you get a 70 ppm. The two figures don't correlate. And in this group, to give you an idea, there's 600 different acid extractions that you could use to extract the nutrients out of that exchangeable pool. In the soluble pool, we've developed 1,000 different extraction agents and systems. So any figure that you look at on a soil test, if it doesn't show you, and they often don't, actually show you what the protocol was used, the information that they're providing you with is basically next to useless. This is an example of a study done of, I think, 3 million soil samples from around the world on a total extraction basis to understand how much nutrition is present in the soils around the world. And when you take any soil type anywhere in the world and extract all the nutrition in that soil, what we found, or what has been found, is that every soil that you look at has all the nutrition already there and available to grow any crop. All it requires is organic matter and aerobic microbes. I added this picture in to get an understanding of what is actually soil and what soil can do and how it functions in the form of when we're talking about erosion. The power of soil is that basically this massive area has had soil blown away, or what was actually technically dirt, blown away, dead soil blown away, because it's lost that organic matter. It's lost the microbial system that holds it together, that supports it. It's not the plant. The plant is growing here because the microbial and soil system needs that, right? That's all functioning. You could have had plants in all this soil, but if the soil was essentially dead, it would have blown the plant and everything away, which is what's happened. And that shows you the sheer amount of soil loss that can happen in these sorts of events over a long history. So organic matter has both negative and positive sites. So we call these anions and cations. So every nutrient in the soil has, or combination, is either negatively or positively charged. Works a little bit like a magnet. So a cation will attract to an anion, a positive to a negative. Something that has 3 negatives will be strongly attracted to something that's got 3 positives. Positive cations, obviously it's like polar opposites of a magnet. If you put the 2 negatives together, you'll actually push the nutrient ions apart. The key to understand here is organic matter actually has the ability, is by far the largest ability, to actually hold on to soluble nutrition in the soil. So if you start losing your organic matter, suddenly you have soil that isn't able to hold on to that soluble nutrition. So the soluble things like phosphorus and sulfur, nitrates are a really big one. Where we start to lack organic matter, we lose the ability to hold those in the soil, and we'll see the consequence of that from the ecological negatives that we find. Anions, as I said, can form bonds with cations. So this has been a mistake where we've put lots of soluble phosphorus into soils that have lots of calcium, and so you get a bond. So even when farmers have put in huge amounts of superphosphate, essentially because of the 3 negative charge that you have with a phosphate anion, it's directly attracted to calcium anion, and you get this incredibly insoluble bond. And without microbial life, you simply won't break those bonds apart. So having put all that fertilizer in, you've still got to bring the microbes back into that system, essentially, to be able to break it apart. So the question has to be, why did we bring it in to start with? Too much organic matter, as I've discussed with many people, can be a problem, because you can end up retaining too much and your soluble pool becomes too large. And again, you end up holding lots of phosphorus. So very often we see really high levels of organic matter with really high levels of phosphorus. And that is very discouraging to organisms like fungi. And then the negative consequences of that are almost endless as far as the soil health goes from the point of view of the negatives that we see associated with just those simple mistakes. So yeah, the big one is excess soluble phosphorus availability disrupts organisms like mycorrhizal fungi and causes them to go dormant.
And I'd just like to say to those people, over the last two Farmers in the Fields sessions, we have discovered that in many of the urban farms which have been producing compost have actually ended up in this exact situation with too much phosphorus in their soils. So you can go back and look at those Farmer in the Field sessions to get an applied understanding of what Daniel's talking about.
Yeah, and it's a very common thing that you know, we simply don't have a really good understanding of the soil system. So it's very easy to put in excess compost thinking that we're doing, you know, great things, but in actual fact, it's all about balance and understanding how the system works as to work how much you need to put in, and it's always a lot less than you think. So nutrient cycling, to sort of understand what's happening in the part of the whole system, and this is a very simplistic model, but it's based around essentially you're getting sunlight hitting the plants, they're generating the energy, and they're feeding they're basically what, as they break down and rot down, they're also a large portion of the organic matter that's been built. But the big thing they do is feed carbon into the soil. So while they feed themselves on sunlight, at this very first level, this is what I was talking about earlier, if those people miss it, first trophic level, this is basically the food chain, levels in the food chain, and plants are what we call autotrophs. So they can essentially, they generate energy and feed themselves. They don't feed on anything. The next trophic levels are organisms that, in this case, they're breaking down, as I was talking, the bacteria and the fungi are largely responsible for breaking down the nutrition and creating that soluble nutrient pool the plants can actually access and feed on. But to release what they have actually fed on, that parent material that created those complex carbons, they have to be consumed. So you've got really important organisms between these nematodes that are feeding on fungi, protozoa feeding on bacteria. I know these arrows are sort of heading in the direction of the trophic levels, but essentially what it's showing is that you've got protozoa feeding on bacteria, the nematodes feed on bacteria, the arthropods, and as you go all the way through, for that nutrition to find its way back into the soluble pool, it's the exudates from things like the nematodes, the worms in the soil, those what we call shredders and other predators that are basically consuming these early stage organisms to release that nutrient. It's part of the whole nutrient cycle that we're trying to get people's heads around.
So when you say exudate, for people who don't know what that word means, essentially you mean like a poos and wheeze, like a waste, isn't it?
Anything that an organism excretes, and whether that be a plant, a bacteria, a fungi, or a human, is an exudate.
There you go.
Right.
Can I ask a question? We have a couple of questions here. This is around simple questions around lessening the organic matter, and I think they've come from our farmers who've discovered they have excess organic matter. Can you add topsoil or sand or clay to lessen the organic matter?
No, well, you can, but what you're talking about now is importing a whole other nutrient stream, and you just simply back at square one to work out what it is you put in. You've already got too much. So by adding more, you don't reduce what's there, you in effect add more. Do you understand what I mean by that?
Yes, including sand.
You don't fix an excess by putting more in.
Yeah, and so sand and clay would be considered still an excess.
It's full of nutrition. What you're lacking in most of those cases when you look at the soil analysis and when you understand it, and this is where we will, the masterclass about how the microbial system really works in full will explain how you actually correct those things. And as I've said, what they're essentially lacking is fungi. It's the fungi to bacterial ratio that is that's out, but that is a subject of a complete whole nother class at the very least. So as I was explaining, plants are producing their simple sugars. They give about 30 to 40% of those sugars from photosynthesis down into the root system as exudates. Again, there's that word. So the organisms that helps the carbon cycle. They then combine that with the nutrients in the parent material, and you create food for the fungi and bacterial life. I included this picture. This is a rose crop quite a few years ago. This probably goes back almost 10 years now. I came from an ornamental background in horticulture, which required me to learn to use an ag chemical manual, which is basically a Bible full of chemistry and solutions. If you had a disease, you looked up the chemical to spray it with and you sprayed it. But when we started seeing that the more you spray those things, the worse you suffer from disease and pest, and the more you have to spray. And it can actually get so bad that the crop will collapse under that poisonous chemistry. What we did as we started this learning process is that we got and evolved a program for the crop we were working with at the time, which was greenhouse roses, which we used to heat, and we used to feed CO2 in a completely artificial environment. And what we did is we introduced beneficial organisms in, and we really followed a very complete biological program, and we eliminated all pesticide use. This is from a program that would have sprayed half a dozen chemicals, three or four at a time, twice a week, every week of the year, fed with heating to control humidity, fed with CO2 to try and get the plants to grow. These plants were growing, and I'll show you the end results of that, far better, more productive, healthier, faster, bigger flowers, longer stems, all those sorts of things. And we completely eliminated any poison in that system. It was all about using beneficial biology. This is, I think from memory, the Waikato with the intersect with, there was another river, I've forgotten the name off the top of my head, I should actually put it on the slide. But essentially what you're looking at here is the consequence of what happens when you turn soil into dirt. The beneficial bacteria, they produce glues that facilitate the formation of microaggregates. So there's small clumps of bacteria, organic matter and soil particles, sand, salt and clay. The fungal hyphae then bind these together as together, these microaggregates together to form larger clumps known as macroaggregates. And as more of those materials are bound together, voids are created. And this is actually how soil structure is formed. Soil structure is not formed with a spade, a shovel, or a rotary hoe, or any sort of mechanical means. Soil structure is the microbial function of the soil. Soil texture is the function of the parent material and the percentages of parent material that are in the soil. But that's essentially what holds it together. So we start to, you've heard of words maybe like crumb structure. So soil with really good crumb structure, it doesn't look like this flat, dusty, dry, it's actually got a real crumb, small sort of aggregates to it. It doesn't look like like fine talcum powder, which is quite often what you see in soil. And here's a really good example or a demonstration. Ignore the words conventional organic. Essentially, you could replace the left organic as healthy soil and the right conventional as unhealthy dirt. And this is what happens when you put that soil into water. All those micro aggregates, all that fungi and bacteria hold that soil together. And there's numerous examples of these sorts of trials to show what actually happens when you compare healthy and what's typically most of the soils that our crops are grown in this conventional model. And that's why we see those rivers running brown with soil. You can have any amount of water crossing across healthy soils and you will not see dirty water coming off that. That is simply a function of poor soil health. So a well-structured soil allows excess water to flow through it. We call it infiltration. Right? So you have that water and air particles, the soil simply doesn't fall apart because it comes in contact with water. But when you have compacted soils, you get waterlogging, and compaction isn't a function of driving a tractor over the soil 100 times. Compaction is actually the result of destroying the organic material, the structure, the microbial structure. So compaction is destruction of soil structure, which is actually the destruction of the microbial system in the soil. And sure, putting heavy machinery over doesn't help that, but the actual reason that soil can stay compacted is because it doesn't have that microbial system to keep this aggregate, this healthy soil structure that we're actually seeing. So you end up with saturated soils basically being able to move and wash away into rivers. I have a slide that describes these two better in terms of looking at when you're talking about, and this is how we have the definition of soil versus dirt. In soil, water, the hydrological process is that water actually travels through it. And can travel through it remarkably well. It's incredible how resilient it is to managing rainfall. So the water is basically this vertical stream that travels down, and you end up with clean water coming out the bottom, which is filling your aquifers. When you actually destroy soil and you turn it into this thing, which is basically just apparent materials, which is a massive clay, which has very little or no organic matter in it, and the microbials have nothing to work with, all of a sudden the hydrology of the soil system changes, and you start getting horizontal movement with water. And so this means that the amount of water getting into the aquifers and to recharge those systems is actually deprived of the water, and we end up with this dirt being carried into our waterways. So this is the function of poor soil health is actually the underlying cause of why we have erosion. It's not about because we haven't, not having plants in the soil obviously is part of the system, but even having plants growing in unhealthy soils like dirt, in this case, is that you're still going to get this massive erosion effect. And that is all just a function of how we've actually treated that soil. Really good example of, in this picture here, of what we look at in terms of a real conventional growing model. We've got this massive distance between the plants. It's just designed to get huge pieces of machinery in between it so they can fertilize and spray it to its last degree and harvest it, where in actual fact it has no basis in science at all. There's all sorts of evidence out there that'll show you in very good field trials that shows you if you evenly space that corn totally evenly across the paddock, you get vastly better result than anything you could ever try to achieve with fertilizer. But what you're seeing here is crusting of the soil. This is just it epitomizes essentially what we actually do to soil, and then try and grow a crop in it. So to grow a crop, you've got to pour on hundreds and hundreds of kilos, in many cases, of highly soluble fertilizers, which the plant can't possibly use, but every time it rains gets washed away. So you have to keep pouring it on. There's no system to hold it. It just has to wash away. And this, unfortunately, is typical for a lot of or the vast majority of conventional agriculture around the world. A well-structured soil, so we're talking about, with all this microbial activity, with high organic matter to support that, acts like a sponge. Those things hold water. The organic matter can hold this is based on 10% organic matter. It would hold the equivalent of 1.7 million litres of water per hectare. So it's actually 170,000 litres per percent. 10% being the ideal level that we're talking about. We can hold an incredible amount of water, and that's water that's available to the plant. And every time it rains, that same organic matter, that soil organic carbon, works like a filter, and so the water that comes out of that system is pure and clean, just like you would if you put it through your own carbon water filter at home, just in a purely natural biological sense. So in that well-structured soil, also plant roots will root much deeper. It always amazes me to find out how deep that plants can root. We have no idea. In many cases, I've struck time and time again in advice that this plant will only root 10 centimeters deep, 15 centimeters deep. So we've got to water it 20 times a day. And then you'll take something like just ryegrass, which we only measure in terms of centimeters, 15 centimeters into the soil, 10 centimeters in soil. In 6 months in healthy soil from a seed, ryegrass has been found to be like 1.8 and 1.9, 2 meters deep down into the soil. That's how rapidly and how effective that root system. Imagine how incredibly how sustainable pasture is that's rooted that deeply versus what we typically have, which is roots of maybe 15, 20 centimeters down. So you've got, even in the case with sandy soil, where water holding capacity is very low, but if simply by taking sand, adding organic matter, and making sure you've got a full microbial system, you can extract that nutrition out of the sand. The beneficial organisms will do that, and they have proven it time and time again. It's just a matter of understanding how that system works. Clay soils, typically very, very commonly known for waterlogging, but how do you fix that? I mean, the typical answer would be that you pile a whole lot of inputs in the form of lots of calcium, and that can help, but all of those inputs are going to have an effect, and all of those inputs can be put in excess, and all of those inputs need to be basically only put in to support the microbial network. It's really the thing we need to be doing to get that soil structure fixed is all about feeding and supporting the microbial system in the soil, not necessarily about piling in enormous amounts of inputs in the form of lime and superphosphates into our soil. It does nothing other than create a system which is totally reliant on you forever putting those inputs in. Sure, you had a question? Or?
No, I was just going to let you know that we're almost at 7:45.
Yep. Almost there. So this is just a quick look at, because people will ask about, obviously you talk about soil, everybody thinks in terms of what's the pH of your soil. Well, essentially just to basically describe it, the pH is purely something involving, largely it's about chemistry. And what we're looking for is to have this ideal level around 6.3. And the reason that we target 6.3 is that it kind of is the sweet spot between all these basic nutrients that are in the soil. So at lower pHs, you have things like iron more available. Aluminium is also more available, which we don't really want. Can cause problems if we have excess aluminium availability in low pH. If we have high pH, we start to struggle to get things like iron. So 6.3 is why we talk about the sweet spot, but it's really in terms of soil chemistry, and it's a guide. It's not really terribly useful. The one nutrient we haven't talked about, and again, this is going to be subject of a masterclass all on its own because of its importance, but this is the one nutrient that doesn't come out of the parent material. Interesting enough, when I talked about the different solubility pools and we talked about the exchange pool, nitrogen comes from the atmosphere as a gas. So above every atmosphere, from memory, there's 74,000 tons of nitrogen above every hectare on Earth. It shows you how much the availability of nitrogen. And if you've got that, nitrogen is supposed to be into the soil using, it's a very complex cycle, but basically it's a biological cycle, and nitrogen fixes that bacteria and they turn it into all different forms, joining it together with carbon compounds and actually putting it into the exchange pool in a mineralized form so it can be held on and held onto in the soil, and that carbon sponge that we talk about in organic matter, so it can be held there and made available as the plant turns it into things. So the biological process will turn it into other forms of nitrogen, which then can be absorbed by plants. But it's a very complex process. It's just interesting that that's the one thing that's actually the misuse of it. Firstly, the excess tillage that went on for thousands of years. We really didn't screw the soil up until we actually started using artificial nitrogens. We really started doing the harm. That combined with our other practices has really damaged our soil systems. And it's just a lack of understanding of how this was actually functioning in the soil in the first place. But again, it's a subject for another masterclass. So we'll try and wrap it up looking at some examples. And basically what we're looking at here is on one side, we've got a paddock that's been treated following a soil food web approach, which is basically just focusing on getting bacterial fungal ratios right, feeding that bacteria fungi in the soil to encourage the ratios, and not using soluble fertilizers. On the right hand side, we're using a normal conventional approach. And the difference is, they're listed at the bottom down here on the left. This one's been grazed 5 times, and this is the same paddock in April 2011. On the neighbour's only been grazed once, and they come back a month later. They've managed to graze 2 more times on the left-hand side of the paddock, and on the right-hand side, even though they've had rain, and you see it's a bit greener, they're still not able to grow enough grass. I'll show you an example of just how much more productive the biological system is than any chemical or chemistry argument or example. This is an example of really poorly depleted typical soils that I would find in horticultural tests. This is out of Pukekohe, but you could find this in intensive horticultural soils pretty much anywhere that you went that have been farmed under conventional or grown under conventional processes. All those bright blue lines that we're looking at, these are all horrendous excesses. We're getting into some big excesses, but these are really astronomical. If you look at under the ideal levels, things like nitrate, nitrogen, we're looking for 10 to 20 ppm. Even that is an excess, but this is kind of the conventional or biological model. Here we started with 564 ppm. We're talking in so many magnitudes of excesses across phosphorus. There's just no chance that you're getting fungal activity in the soil. So we took that soil and we stopped putting the negative inputs in it. That was 2014. And this is the results we got in 2019. And obviously, to a large degree, we've got rid of many. We've got a little bit more problem with sulfur. And it has to do a little bit because we've been putting in potassium sulfate because we've got this massive sodium problem which was coming from their bore water, which we've now corrected by using rainwater and using rainwater storage for that purpose. And so it'll be interesting to see what happens this year. But the results of fixing that soil were basically, they ended up of the same area, they increased their production 175%. The cost of their inputs are down 78%. Their profit was up by 250%. The decrease in pests and diseases is literally non-existent. These are crops that used to get sprayed twice a week for endless pest and disease problems. It was just seen as normal. There are diseases that cost them a fortune in crop losses. Their cost of that control, that's why their input costs are so far down, because they literally do not have pest and disease issues. And things like crop life expectancy, where they would typically have to replace the plant every 5 years, now we're looking at 10 years. And that's a frequent sort of experience that we're having creating these sort of healthy soil models. It's just...
I'm going to ask you a question now, which is actually asked by Rebecca at Dignan Street. And they're saying that their organic matter is 25%. I'm actually going to read it to you. So I get it right. Our site had 25% organic matter and was built up predominantly with wood mulch carbon, which was wood mulch carbon rich and therefore fungi rich. So we are baffled how the fungal levels are low. And I think that's a good place to ask that question because we've just actually discussed why.
Okay. So it is itself a subject again of a whole other masterclass but the simple thing is that you would have generated that compost using probably relatively conventional aerobic systems, but quite often they turn those aerobic compost piles sometimes twice a week to keep the temperature down and to keep them aerobic. That process actually destroys the fungi. So what you actually generate, quite often what you find is theoretically it should be high in fungi, but an actual process of how you develop that is what you'll find is that you actually are quite deficient in fungi. When you have an excess of those soluble nutrients, there's a whole range of reasons why the fungi could be present. In fact, I guarantee they're present, but they're just dormant. They're sitting there not doing anything. And typically what we find in those massively high organic matters levels is that you have lots of woody material sitting around just not breaking down. And that is a clear sign amongst others that you actually lack fungi. So in theory, I understand, you know, the wood-based piles should be generating, you know, good fungal compost, but it has an awful lot to do with the other ingredients and the processes put in place, and the end result of whether you support, you know, how that's being supported. But that whole soil analysis is kind of, for an example, and composting is really has to be the subject of another conversation or another masterclass. So
I think they were talking about wood chip though, Daniel, not compost so much.
I understand that, but that's really a subject that we have to cover at another time, because we're going to run out of time here as we are. So here's another example of where we've simply fed the soil here, which I know is deficient in calcium and phosphorus theoretically on a chemistry basis, and all we did was we put beneficial aerobic microbes in here, and we put food sources like a little bit of kelp and a bit of fulvic acid and other bits and pieces in there to support those organisms to be able to do their job. And the growth difference, as you can see this, at times where we've done this, we can come back 6 months later and still see the difference. You know, it's just amazing what you can do if you just simply feed the microbial system, re-inoculate soils. You couldn't achieve a better result if you poured 100 kilos of urea on the soil, except for on the left was be all positive. There's no harm being done here. It's all about supporting the microbial system. So they've got the last two more slides, and the real interesting thing, I added this in recently as I've been sort of further studying this, looking at, I wanted people to understand an example of how productive land can be, because I often talk about with people what actually is capacity to grow or produce on an area, and the numbers are often I come up with probably scare people, or they think I must be kidding. This is an example. This was data that was I came across recently, and there's a few other bits and pieces that's interesting here. But essentially, what we're looking at down here in cultivated land, this is the average biomass produced per square meter per year above the ground. So that's essentially largely the results of the photosynthetic crop that's been grown above the ground. These are the results that they get per square meter. And when they compare that to a rainforest, which has never had anybody add compost to it, or bring in nutrients to it, or add fertilizer to it, fortunately not done any of that, it's actually, you can see the amount of productivity. I mean, it's three times greater in its biomass production. Swamp and marsh, similarly, you're looking at that sort of figure. There was a kelp marine figure here earlier on, which is about 2,500. So, you know, we know kelp forests incredibly productive. What we're looking at here, this is basically a biological approach. All what we're talking about is using the science that I've been talking about today, using biology and working with fungi and bacteria and organic matter in that soil. And you're looking in this transition. This isn't the first year. This is what they've achieved in the first year. They've also got carbon figures going into that soil, how they've increased it as well. But I'm looking at the biomass figure. When you do that for 3 years, you know, we're just so far beyond, you know, where we are with our current cultivation practices. It isn't really even funny. It's actually incredibly depressing how inefficient we are in comparison to what nature can do. And we're 6.5 times greater in our productive capacity on those same soils if we actually treat the soil using, you know, the soil function as it's designed by nature to do. One last slide, and then we can wrap it up for some questions, is I came across this, and this was really important. This was looking at our food production in relation to fossil fuels. And you would think that over the last 75 years, this is from 1940 to 2015, that we would have become, we must be more efficient at producing food than we've ever been. I mean, we've got machinery, the scale, everything we must be producing more food. But it's interesting, we're actually 23 times less efficient at producing food in relation to the amount of fossil fuel. So we're using, back here we were using 2.3 calories per calorie, 1 calorie of fuel, fossil fuel used. 75 years later, we're down to 0.1 of a calorie per fossil fuel calorie used. It seems amazing that the thing that we actually need more than anything else on this planet, which is food for us to survive on, is now so inefficiently produced on the one thing everybody agrees that we're running out of, and that is the fossil fuel to actually grow it. That's it from me.
Wow,
So,
Daniel, you got that in under an hour, which is absolutely fantastic. So we have time for a couple more questions. Martin gave us a question of which are realizations. So it's all about fungal. I'll read you the question actually. So the answer is to feed the microbial system. How do you easily and cheaply do this? And as I said, we'll cover that in the next masterclass. But also, we do have during the week Regenerate Now Instagram, where the farmers who've been working with us for some time are actually discussing this, and also the farmer in the field, which you can actually go back and look at on YouTube, which also discuss some of this if you're desperate to enter this conversation tonight. So just to give a bit of a rundown on the things that we actually covered today, which is the understanding that any input, including compost, can be done and applied in excess. The amount of nutrition that a plant actually needs is vastly less than we think they need. That it's that microbes deliver nutrition to the plants from the parent material. And the biodiversity of microbes is the key to health of the plants and the soil. And the thing that I'm really struck with tonight, Daniel, is that diagram that just shows how incredibly productive these systems can be. Almost twice the amount of a tropical rainforest. And so when we call on the Regenerate Now program, what essentially is everyone, everywhere, all at once, let's regenerate now. Let's create a systems change in 3 years to help our climate recover from the climate change issues that we have. You can see that this is a very realistic proposition. And thank you very much for joining us tonight, because by learning about these things, you are becoming the enablers of that transition. So thank you very much. Are there any other questions? Just much gratitude, Daniel.